Hi, I'd like to do a few examples with you finding the complex zeros of polynomial functions. The directions for each of the problems will be these. State all the complex zeros of the function, state all the x-intercepts of the graph of the function, and show the complete factorization. And let me remind you what complex numbers are. It says complex zeros, and sometimes people misunderstand and think we're only talking about the non-real zeros. Remember, the set of complex numbers is made up of our real numbers and our non-real numbers. So our non-reals are any numbers that have an I in them, like 5 plus 2i, or I times the square root of 11. Let me break down the reals just a little bit further. They could be broken down more than this, but remember the reals also can be broken down into our rational numbers and our irrational numbers. So you do need to know what number sets people are talking about. Remember, our rational numbers are numbers that can be written as a fraction like 2/3 or -5/11 or 14. Our irrational numbers could look like square root of 5 or 3 minus the square root of 11. But when we're asked for the complex zeros, that means all the zeros, real and non-real. So here we go. Here's the first problem. We will have f of x equals x cubed plus x squared minus 13x plus 3. I always consider my traditional strategies first. I consider whether I could factor that one by grouping. It doesn't look like it. So now I'm to my rational zeros theorem, and I list the possible rational zeros. If it doesn't have a rational zero, it will be beyond the ability of in this video, to find them. So we have factors of 3 over factors of 1. So plus or minus 1 or plus or minus 3. With direct substitution, I hope you can see that 1 is not a zero. 1 plus 1 minus 13 plus 3 doesn't equal 0. I don't really care what it is because it's not 0. Similarly, you could tell that with -1, but let me just do the synthetic division in case you have a hard time seeing that. So I'll do the synthetic division with -1. 1, 1, -13, 3. So we'd bring down our 1, multiply and add, multiply and add, multiply and add. So in fact, we know that -1 is not a 0. And we know that f of -1 in fact would equal 16. Let's move on. We'll try 3. So let me write the coefficients here, and here we go. We bring down the 1, multiply and add, multiply and add, multiply and add. Oh, this time we do have a remainder of 0. So it means, yes, we have found a 0 for the function. So we know the polynomial function can now be written as f of x equals x minus the 0. So that's x minus 3 times the polynomial we get from these coefficients. We know it's a constant, the x term and the x squared term. These are the coefficients. So I have x squared plus 4x minus 1. Now at this point, I always feel like I'm home free when I have it boiled down to a quadratic polynomial, because I don't need to use the rational zeros theorem. If I can't get it to factor in my traditional way, like setting up my parentheses and factoring it this way, then I know at the very least I could use the quadratic formula. But let's see if I need to. It doesn't factor just using my trial and error, but to find my zeros, I know I can set x squared plus 4x minus 1 equal to 0. And now with that quadratic equation, I can either use the quadratic formula or complete the square. I'm going to complete the square because notice our leading coefficient is 1 and our middle term is even. So we'll add 1. Take half of 4, it's 2. 2 squared is 4. We add 4 to both sides. So I have x plus 2 squared equals 5. And when we take the square root of both sides, we have x plus 2 equals plus or minus the square root of 5. Or x equals negative 2 plus or minus the square root of 5. And notice, of course, over here we have x equals 3, which we knew we had because we could tell right here that 3 was a 0. So let's answer all the questions. State all the complex zeros. So let's do that, the complex zeros. And notice in this problem, all the complex zeros are real. They are 3, negative 2 plus the square root of 5, and negative 2 minus the square root of 5. Let me separate it from my little chart over here. So one of the zeros was rational and 2 of them were irrational, but still all 3 are real. And of course, that means they are also complex. Let's go on. State the x-intercepts of the graph of the function. If the zeros are real, they are also x-intercepts. So the x-intercepts would also be 3, negative 2 plus the square root of 5, and negative 2 minus the square root of 5. I'm going to even write them as ordered pairs. 3, 0, negative 2 plus the square root of 5, 0, and negative 2 minus the square root of 5, 0. So if we were going to graph this polynomial function, the graph would cross the x-axis at those points. And last, it asks for the complete factorization. So we know f of x equals x minus 3 times x minus negative 2 plus the square root of 5 times x minus negative 2 minus the square root of 5. And I always peek at my coefficient and look to see right here that the coefficient will be at 1x times 1x times 1x, that's 1x cubed, and yes, that's what I needed, a 1x cubed. So there isn't any other constant up front here that I need to worry about. I know it's just a 1. But it is a little bit nicer to get rid of the double sets of parentheses, so let me just take one last step here. I'm going to have f of x equals x minus 3 times x plus 2 minus the square root of 5 times x plus 2 plus the square root of 5. And we have the complete factorization done. Here's our next example, same directions. Let's get started. So we're trying to find all the zeros, x-intercepts, and the factorization for this polynomial function. This one I want to remind you, don't forget about your old strategies, your traditional strategies of looking for a common factor first. Do you see that there's a common factor of x? So let's take that x out, and we'll have f of x equals x times 3x squared minus 2x plus 11. And then I feel home free. I'm down to a quadratic. I always try to see if I can factor using my traditional strategies. And very quickly with this 3x and x and 11 and 1 and 1 and 11, I see I'm not going to get that 2 in the middle. So I erase that. And know I need to use another strategy. Let's see, to get this broken down, then I would set 3x squared minus 2x plus 11 equal to 0. I'm not going to choose to complete the square this time because my coefficient here is 3. And to make it be a 1, I'd have to divide by 3. And the numbers just don't look very friendly for that. So I'm going to use the quadratic formula. So we have the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2a Let's keep simplifying. We have 2 plus or minus the square root of 4 minus, let's see, that's 12 times 11, that's 132, divided by 6. Still have a simplifying job to do. Let's rewrite this with I, and we'd have 2 plus or minus 8i square root of 2 over 6, which is reducible. And I have 1 plus or minus 4i square root of 2 all over 3. So those are 2 of the zeros. Let me remind you that the number of zeros will match the degree. You might have some duplicate zeros if you have a zero of multiplicity 2 or 3, but we don't have that in this case, so I should have 3 distinct numbers. Notice the third one comes from this. I didn't write it down, and I will right now. This gives us x equals 0. So let's make sure we very clearly answer the question. The complex zeros right here are 0, 1 plus 4i square root of 2 over 3, and 1 minus 4i square root of 2 over 3. In this problem, we have 3 complex zeros. 1 is real, and the other 2 are non-real. So that brings me to the x-intercepts. What would the x-intercepts of the graph be? Well, they must be real. So this 0 would be generating an x-intercept. So we have an x-intercept at 0, 0, but the other 2 zeros are not real and hence do not generate x-intercepts. So the graph of this function would just cross the x-axis in one place, and it's at the origin. Let's show the complete factorization. I'm going to write down here so I have enough room. So I have f of x equals, we have our x right from here, and we have x minus 1 plus 4i square root of 2 over 3 times x minus 1 minus 4i square root of 2 over 3. And it is very tempting to leave it that way, but I mentioned on the previous problem, you must consider the coefficient right here. If I were to multiply this out, I would have a 1x times a 1x times a 1x. That is 1x cubed. Look back here. It is a 3x cubed. That means this factorization is missing a factor of 3 right here. Let me write it in red here to point it out. That 3 is important. Now, if you were to multiply that out, you would in fact get the original function, but without the 3, you would not. And it would be a nice challenge problem to multiply that out and make sure that it does equal the original function, but in fact it will. I'll make this our last example. I thought we'd do a 4th degree problem this time. So f of x equals x to the 4th plus 6x cubed plus 13x squared plus 30x plus 40. And I don't see anything about our traditional strategies that would help. So I'm going to jump right in with the possible or potential rational zeros based on our rational zeros theorem. We know the numerator must be a factor of 40 and the denominator a factor of 1. So plus or minus 1, 2, 4. Let's see, 5 goes into 40. 6 doesn't, but 8 does. And so does 10, and so does 20, and so does 40. Wow, I hope I don't have to go too far into that list. But let me point this out. We're trying to find a number that would make this function equal to 1. Notice if you just choose 1 and we try positive 1. If you pop it in, you'd have 1 plus 6 plus 13 plus 30 plus 40. Do you notice that all of these numbers are positive? So if we put a positive number in here, any positive number, the result is going to be positive and not 0. So that actually eliminates all the positive numbers for this problem. I'm not going to even try those. So I'm going to start rolling through the negative ones and see what we come up with. So let's try -1. See if it's a 0. 1, 6, 13, 30, 40. So here we go. Bring down my 1, multiply and add, multiply and add, multiply and add. Whoop. Multiply and add, and that's a no. It is not a 0. Let's move on to -2. Let me write down my coefficients, and here we go again. Bring down the 1, multiply and add, multiply and add, multiply and add, multiply and add. Ooh, now we do have a 0. -2 is a 0 for this polynomial function. So let's write our factorization where we are right now. We'd have f of x equals x plus 2 times this polynomial x cubed plus 4x squared plus 5x plus 20. Do you see where those coefficients came from right here? So let's continue. Now it's tempting to use the rational zeros theorem on this polynomial right here. No problem, we could do that. But I want to remind you to always consider your traditional strategies. I see this. Do you see that this might factor by grouping? Well, give it a shot. If it doesn't work, I'll come back and I'll try to find another 0 on my list of possible rational zeros. But let's do this. We're going to bring my f of x down. I'm going to try to factor by grouping. So I have an x squared times x plus 4. And I have a 5 times x plus 4. So this looks good. And this is one reason I wanted you to see this example. Our traditional strategies still work. So f of x equals x plus 2 times, let's see, we take out our common factor of x plus 4, and we have x squared plus 5 for our other factor. This factor right here does not factor over the integers, but we do know that you can set x squared plus 5 equal to 0 and solve that equation. So we get x equals plus or minus I square root of 5. So here are my list of zeros right here. Let's write it very clearly. State all the complex zeros. Let's list them. They are -2, -4, I times the square root of 5, and -I times the square root of 5. And notice in this list, 2 are real. They are also rational. And 2 are non-real. That means our x-intercepts would be just -2, 0 and -4, 0. And our complete factorization would be f of x equals x plus 2 times x plus 4 times x minus I square root of 5 times x minus -I square root of 5, which is x plus I square root of 5. And I'm looking at the coefficient here. It's a 1. And if I multiply x times x times x times x, that would be a 1x to the 4th, just like we needed. So this one is done.